Yeah, we are excited about ZHFE. We think it's just a neat idea. Think it's a very clever idea, and just a fundamentally new way of constructing primitives. I think Alan mentioned in the talk before ZHFE a little bit, the construction. So I wanted to say something to start off about multivariate encryption in general, some of the pitfalls inherent in trying to achieve encryption with multivariate schemes, and also some of the tools that we use to construct these technologies. So the first thing is, I think it's useful to think about large structure schemes. So there are small structure schemes, right? Like small field schemes, thinking of signature schemes, like oil and vinegar, unbalanced oil and vinegar, rainbow, this sort of thing. For a lot of these schemes, it's useful to use some type of large structure, and that doesn't have to be an extension field. It just has to be some large structure where you can use a multiplicative structure to get something that's nonlinear. So the way these work is you start with a finite field FQ. You consider some sort of algebra A over it. Why in algebra you need to have a multiplication. You also need to be able to look at a vector space representation as well. Okay, so then you use the multiplication in this algebra to define some particular nonlinear map, and your nonlinear map is going to have one multiplication for each summand, right? It's going to have one instance of a multiplication in that structure for each summand. And then what do? You perturb the vector representation of that function. So this algebra A, we've seen it in a few different ways of using this, of defining this algebra. So one of them would be, the original, the superstar, especially here, in Japan, the superstar among the big field schemes, the Matsumoto Imai scheme, we commonly call C star. So what's the structure here? You're using an extension field. Okay, so extension field has a nice structure. You can utilize that and use multiplications. The same thing for HFE. For HFE, you also use an extension field structure. The ABC matrix scheme, so Alan also mentioned that one. This one was very interesting because this one is using a matrix algebra, right? It's using a matrix algebra over your base field. And that's a new idea. That's an exciting idea. And then ZHFE. So ZHFE is again using this extension field structure. So with the ABC matrix scheme, we actually see that we don't even need to worry about commutativity, right? You're not using a commutative algebra, right, over this base field. You just need some algebraic structure to give you a multiplication. So it's quite interesting. All of these schemes retain information about this extension structure. And that's the fundamental challenge in this science, just to figure out how to hide that structure, how to do it effectively. And historically, we've not done a great job with many of these schemes, especially when we were focusing on encryption. Encryption is just hard. So why? why is it hard? Well, one thing is you need to be able to get a unique preimage. And so if you're restricting yourself to have the same size output for your map as input, then you're horribly restricted in being able to have an essentially injective map. So we might say that a function is statistically injective if the probability of choosing an input for which there's another input that gives you the same output is below some threshold, some predetermined threshold. Okay, something that allows like decryption failure to almost never happen. And how can you possibly achieve this? Well, inflation. Inflation is how you can achieve this. Just many of these new schemes have double the key size. This doubles your input size, right? Double the key size, double your output, make it twice as big as your input. So I was thinking about ZHFE and wondering, well, could we do any better than double the key size? And could we do something to affect this structure, the extension field structure that it relies on? And maybe fixing the double key size, maybe that also is part of the solution for getting rid of this structure as well. Okay? So I started thinking about if I could remove some of equations. So the first thing I did is I looked at, let's look at the scheme. Let's look at the scheme first. So this scheme, this is the extension field structure, and that's our algebra over FQ. It's an n-dimensional extension. And the way you construct a key for the scheme is you construct two quadratic functions, f0 and f1, from this extension field to itself. Okay, and you have to select them so that this equation here at the bottom is satisfied with psi having a restriction that you have very low degree. Okay, and so you can see you have this f0 and f1 embedded in that equation over there. Those are quadratic. They have linear maps applied to them, the L00, L01, etc. And then you multiply by another copy of x or x to the q in the extension field. Both of those are linear in the coordinates of x. Okay, so you get something that's actually a cubic map. Okay, psi is now a cubic map with a degree restriction. Okay, so what are the public and private keys? So privately, the user keeps track of psi and these linear maps Lij, and publicly you concatenate, that's supposed to be f0 and f1, you concatenate those and do the butterfly construction. You have an affine transformation T that mixes up the outputs, affine transformation U that mixes up the inputs. So how do you actually achieve decryption? You take an output Y, you find the preimage under T, right, because it's a non-singular map. Then you parse it into two elements of the extension field, V0 and V1. You know these are the outputs of the functions f0 of u and f1 of u. So the hard part is now how do you undo that mapping of f? Well, you rely on psi, okay, that map psi that we had before. So here I'm writing out psi of u, and what it actually is an equation, right? Psi of u is exactly this quantity. Now what do we see in here? We see f0 of u, we see f1 of u, okay, they're highlighted in red now. But those values, they're just constants for us now. We know them, they're v0 and v1. So we plug those in for those values, right? And now, look what we have on the right-hand side. Our u, which is the preimage we're looking for, it only occurs at the very small degree on the right-hand side. U, that's degree 1, the u to the q term, degree q. Well, that's less than the degree bound for psi, so you can use Berlekamp. Just move your equals to the other side and put a 0 on the other side, right? And you can use Berlekamp to invert that and find preimages. Then you can test and see if you get a preimage that actually is compatible with what your output is. Okay? So a question is, how do you know that there exists f's with this property anyway? How can we compute these things? Well, if you look at the relation, psi, it's cubic, but the coefficients of the cubic occur linearly in this equation, right? The coefficients occur linearly on the left-hand side of this equation. What about the right-hand side of the equation? We have these linear maps. We don't know their coefficients, defining them as linearized polynomials, but there exist coefficients for them, and they are occurring linearly on the right-hand side, right? The unknown coefficients of the quadratic maps f0 and f1, the coefficients, they occur linearly on the right-hand side. So what do we get? We actually get a bilinear relation, system of bilinear relations in the unknown coefficients of psi, Lij, and fi. So set the Lij's, set their coefficients to whatever you want, randomly. You can even fix psi if you want, and you can solve for f. And so it's interesting to think about the degrees of freedom you have in selecting different pairs f0 and f1, even for fixed psi and Lij. I think this is very interesting. The only term that's important here in the expansion of psi is the cubic one. The other stuff we can handle with affine transformations and such things. So to look at roughly the degrees of freedom we have in selecting a pair f0 and f1 for a fixed psi and Lij's, we have n squared plus n unknown coefficients of the quadratic maps, and we have n squared equations defined by the first double sum and here. And so that implies that we have a solution space of dimension n over the extension field of maps f0 and f1 that satisfy this equation for fixed psi and Lij. Okay, that's a pretty big space if you think about it. That's pretty interesting. We have lots of degrees of freedom. Maybe we can do something. Take away a little bit of degrees of freedom, not getting rid of entropy, not getting rid of so much entropy that we're in trouble, but maybe we can remove some equations. Okay. Before we do that, though, it's easier before you deal with the minus modifier to analyze original schemes without the minus modifier. The algebra is easier. So I want to revisit the security analysis of ZHFE. Okay, so the first thing I want to talk about is differential symmetry. One of the reasons I want to talk about it is I just like the math involved in it. It's fun. But I think it's actually a legitimate concern. If you look at the history of multivariate crypto and how schemes are broken, there are some properties that are maybe somehow the most, how do you say, they're the most inherent. They're always present and haunt us with trying to get security in multivariate. I think QRank is, it's at least evolving as the principal one that we have to analyze. But if you look at the actual history, look at the number of schemes broken by different types of attacks, you'll see there's actually a fair amount of dominance for differential attacks. Differential symmetric attacks, differential invariant attacks, and a lot of attacks that you weren't even written originally as differential attacks, you can see them as differential attacks if you look at it in the right light. The original attack by Pataran on C star. Okay, this one you can see as a differential attack. In fact, you can extend that differential attack as another way of breaking, you can extend the differential attack that broke S-flash into something that breaks the original scheme as well with a different technique. Balanced oil and vinegar. There's a differential, the Kipnis-Shamir attack actually is a differential attack. It's a differential invariant instead of a differential symmetry. I'll talk about that in a minute. But there are very, very many schemes, LIC minus, many of them, that the differential attacks were of great concern. So here's something else that might make you alert. Consider this map. I was thinking, can I come up with an example where a differential symmetry exists for a not entirely trivial map? This is actually kind of a trivial map, but I can come up with ones that are not trivial and still find differential symmetries. So I decided, okay, I'm going to do this as an exercise on paper, and I chose a degree 6 extension of an arbitrary finite field FQ, and I sort of randomly it literally means out of my head, not with a computer or something, spit out the first polynomial that my hand wanted to write, okay? And then I said, can I find a differential symmetry for this? And it took probably about 5 minutes, and I found this map. Okay, so that's not 5 minutes of CPU time, that's 5 minutes of very slow CPU time. And I was able to find this, and I think this is actually a very interesting one. This map, it does induce a discrete differential symmetry. And interesting is the coefficients here, the restrictions on the coefficients. You have to have a beta here in the base field, and this alpha is actually in an extension field, but contained within, properly within the big field. I think it's very interesting that this exists. This particular one, this is not a multiplication, right? So that's why. This is not a monomial map, but this is not a multiplication. So it can exist. If you have if you're looking for multiplicative symmetry, which is what my theorem was, that's where you're insisting that these L maps are multiplications. That can only exist if you have a monomial map. Okay? But anyway, it's not important. That's not important. Okay, so if you look at the public key, you can derive information about psi this way. I mean, we really just have some linear map applied to the public key in a few different places. And we have u of x plugged in instead of x into psi. You get this relation, and so now you can look at what happens when you take a differential. Now, psi is actually a cubic relation, and so if we want to get to the linear algebra and being able to separate variables, instead of just taking a differential, which would give you something that's biquadratic, you should take a second differential, and that'll give you something that's trilinear. Right? So this is what it looks like. It couldn't be simpler. You know, it's very pretty, very symmetric. And the thing about this is you would like to be able to solve a sort of min-rank problem on a 3 tensor in order to try to extract what your linear maps U should be. And it's not exactly clear how to do that. I mean, I can't say that I completely prove that it doesn't work. It's just when you do this, you actually are solving a rank problem on a 3 tensor, and computing rank for 3 tensors is already tough. So it doesn't give us a lot of hope, but I do hope that in the future something like this actually does go to give us an attack on ZHFE, because that would advance our science. I would like that if that occurred, but I just don't see how it would work. Okay, then the other aspect of differential attacks we need to address for ZHFE is differential invariant attacks. So the prototypical example of a differential invariant attack in my mind is the attack on the balanced oil and vinegar. What happened there is, if you look at the differential of every public polynomial for balanced oil and vinegar, they all send one particular subspace, the oil subspace, to the vinegar subspace. Every single one of them. So you have a list of many, many maps, and all of them have the property that there's one special subspace that they all send simultaneously to this other subspace. That's extremely weird behavior. And when that happens, you can actually just compute it. Okay, their technique for computing it was invert one of the maps, and now you have an invariant subspace for that map. You find that, you find the oil subspace. That's the prototypical idea behind a differential invariant attack. Now, for us, all of our information about the scheme is wrapped up in the psi map, which is cubic. So we can't use that definition directly because it's just not appropriate. We need to use a second differential to get something to become linear, right? Trilinear, right? Whereas with OV, when you have something quadratic, you just take the first differential. So this is the most general form of extension of differential invariant that I've come up with. I've come up with a few. This is the most general form. That is to say, other forms are special cases of this. Okay, so a differential invariant of a cubic function is a pair of subspaces, V1 and V2, so that there exists a subspace W whose dimension is less than or equal to the minimum of V1 and V2, so that for every matrix in the span of the differential coordinate forms, this trilinear function vanishes for for ABX in V1, V2, and W perp. So a way of thinking about this is, if you select your space V2, you're putting in different values B, and every time you plug in a value B, you have an induced bilinear form in A and X. So you find a subspace of bilinear forms by selecting a subspace B, and what property does that subspace of bilinear forms have? It has the property that if you restrict one input to within the space V1, it maps you to the space W. So then if you take a dot product with something in W perp, you get 0. This is something that we can use actually computationally to try to derive such a structure. Okay. Okay, and so for analyzing this, there's some nice fun little techniques, but here I have A hat, B hat, and X hat in V1 and in V2. I'm calling them hat now because I'm actually already considering them to be the image of a projection map from the entire space. Okay, but the existence of this differential invariant implies that the second derivative of psi evaluated at these coordinates, where S is a surjective map from V2 onto W perf, you have to get 0 out of it. If we expand what that means, we get this system, or these cubic monomials, the sum of these cubic monomials. Okay, now the interesting thing is, because of this degree bound, and since log Q of D is so much smaller than the dimension of the VIs, this collection of monomials, the A hat to the Q to the I, B hat to the Q to the J, is independent in this quotient space. And what that means is, when we look at this polynomial, we can consider the alpha I, J, L, S, X hat to the Q to the L. We can consider those to be coefficients of these monomials, and for the entire polynomial to be 0, every one of those coefficients has to be 0, right, by the linear independence. So we get these equations. For each fixed I and J, we have that this linear map is evaluates to 0 on S of X hat. And that implies that with very high probability, because we have a lot of actually random coefficients, alpha I, J, L, giving us a lot of random linear maps, and we're in the common kernel. So it's with very high probability that we're 0, and that means that S is the 0 map on V2, But we just said that S was a surjective map onto W perp. So if S is the 0 map on V2, on the domain, that means W perp is 0. That means you have a trivial differential invariant. You're not getting any information about the structure of the scheme because every map has that property if you insist that one of the spaces is 0. Okay? So there is no invariant structure for you to exploit in an attack either. Okay, now the Q rank is where things kind of start to go south fast for ZHFE. The Q rank of a homogeneous quadratic map is the rank of the quadratic form associated with the map. I don't ever really think of it that way. I like to think of it as the minimum in the isomorphism class of the polynomial of the rank of the associated quadratic form, because then it's isomorphism invariant, and that's more useful to us. Because as you mentioned before in your talk, with Grosvenor basis algorithms, if you have this trick that your T is increasing the Q rank, the Grosvenor basis algorithm will automatically pull back the small Q rank thing anyway. So I think it's better if we think about it as being something invariant in the isomorphism class. Okay. So if F is a quadratic map, I'm just listing out the coefficients here. You can write it in this way as a quadratic form, and then take the rank of the matrix if you want. Actually, so here I'm clearly not in characteristic 2, but if you're not in characteristic 2, then you can diagonalize this. There's a basis which gives you a diagonal form for this, and then it's just the number of non-zero terms. That's going to be the rank. Okay, so here's where it gets interesting. We know that psi has a small degree, right? Psi has a small degree, so therefore it has to have a small rank, cubic rank. It has to have a small cubic rank. But look at the terms that you get from L00F0x plus L01F1x. Okay, the F0 and F1, they're supposed to have very high degree terms and fairly arbitrary, right? But you apply these linear maps to them and multiply by x, you have to get a lot of cancellation with terms over here that are being multiplied by x to the q. So in particular, let's just focus on one of these terms, the L00F0, L01F1. If we write it as a quadratic form in this way, we derive that the alpha ij has to equal 0 whenever it's the case that I and j are not 1, and the sum of q to the I plus q to the j is greater than d. Why? If we are a term that such that q to the I plus q to the j is greater than d, and I and j is not 1, we can't cancel out a product x times that term with anything on the other side, and we would have high degree terms inside. Okay, so they must not exist. Those coefficients must be 0. So we can revise our view of this quadratic form. It really looks like this. That doesn't have high Q rank, right? That's the punchline. It does not have high Q rank. I think this may need to be a floor, not a ceiling here, but it does not have high Q rank. Quite obviously, right? It does not have. So here's the thing. If I have any full rank linear map on a system, I don't decrease the Q rank. I don't decrease the Q rank by mapping with a full rank linear map, at least not this isomorphism invariant version. I don't decrease that. So this is the Q rank of the scheme, and so that's problematic. I haven't actually developed this into a full attack, by the way, but it does not give you security. I mean, you can't guarantee security from this. So what about if we make the L maps singular? Then we no longer have as harsh a restriction on the Fs. We still have to have the condition that this particular map here, the L00F0, it still has to have this structure. It has to be this way. But if you relax the conditions on F by making the L maps singular, then you can potentially get higher rank for F0 and F1, which are what actually are embedded in the public key. So that's the idea of how to fix the scheme. All we have to do is let the Lij have non-zero co-rank, something reasonable, and then you can actually have higher rank for the F0, F1 system. That's the trick. Okay? But I feel like like I said, I haven't actually developed this into a full attack on ZHFE. This is more Ludovic's domain, I think, the attacks. So maybe somebody's interested in doing that, but at least you can't really have a lot of confidence in the scheme if the Q rank is low. Right? So degrees of freedom for ZHFE. This is how we construct the minus modifier. We look at degrees of freedom. So imagine F0, instead of being from FQ to the N to FQ to the N, let it be FQ to the N to FQ to the A, F1 FQ to the N to FQ to the B. So you have A plus B dimensional output instead of 2N. How small can we get that? Let's call that N plus T, because we know we have to be at least N, right? And we'll try to minimize T, still keeping enough entropy and also degrees of freedom for it to be able to solve for the coefficients of F. Okay, so if we look at it this way, the question is how many choices of F0 and F1 will satisfy such an equation with degree bound on psi? Okay, and it's just a matter of counting the coefficients. We have N plus T times N plus 1, choose two unknown coefficients. We have a bunch of linear constraints to satisfy the structure of psi. This S here is the number of non-zero monomials in the expansion over the extension field of psi. And down here we have some more linear relations because we require that the LIs actually have a co-rank C. Okay, and if we look at these, we only need to find the smallest t, more or less, such that N plus T times this quantity, right, is greater than the number of linear constraints we have on the system. And you can do the arithmetic, and T equals N minus 2 works in general. We can't do any better than that. So what does it mean? It means we can remove 2 public equations. We can remove 2 equations and have it a little bit smaller. So maybe that's not as impressive as the minus modification in the previous one, but I think it's interesting that, at the same time we have this independent ideas of doing the minus modifier for encryption. I think that's very, very, very interesting. It means there are a lot of new doors opening to us with this idea of this inflation blowing up the output space. So the security of HFEV minus, you can actually bootstrap directly from the ZHFE analysis. So for the differential stuff, the only thing that's really much harder is the differential invariant analysis because you get so many extra terms to deal with. But all that has an effect of doing is changing the probabilities. But it still follows through. Degree of regularity. So the degree of regularity, think about it. If I have a system of equations and I remove some equations, what happens to the degree of regularity? It either stays the same or it gets bigger. Why is that? Why is that? Because if I remove equations, I'm potentially removing non-trivial syzygies higher up in your calculations. So there's a bound in the direction that favors us for removing equations as far as degree of regularity. What about Q rank? Well, the Q rank, like I said, we can take care of that with the L maps. Okay, there is some potential that we drop the Q rank from a projection, removing some things, but the L maps, I think we can take care of the Q rank that way. Okay, so then parameter selection. We selected some parameters for the system. We need to worry about the Kipnis-Shamir style of attack. We can select the co-ranks to preclude this attack, and also it'll help with being secure against algebraic attack because we get the Q rank high enough. So here are the parameters we actually propose for the scheme, and we are very aggressive with these parameters, very aggressive, to the extent that maybe this is borderline breakable, and hopefully somebody can break it to advance the science. But here, what are all these numbers? Q is the size of the base field, N is the degree of the extension, D is the degree of the polynomial, psi, R is the number of equations that we're removing, and C is the co-rank we insist that every one of the LIJs achieve. Okay? And so then what is the effect on performance for this transition from ZHFE to ZHFE minus? Well, let's compare it directly to ZHFE, the exact same system with the same co-rank L and everything, without removing equations. So for encryption, it's about 2% faster. So the reason it's 2% faster is because you have 2% fewer equations. Key size is 2% smaller because you have 2% fewer equations. Decryption is nearly identical because you're doing the same calculation. You're doing the exact same calculation. It's a Burley camp on the psi, right? Nothing's changed. It's even over the same field, so nothing's changed at all. The public key size for this particular scheme, the 108 ZHFE minus, is 63.1K. I'm not sure if we can do any better than that or not. We'll just have to see in future work. Okay, so I would love to see more work on this scheme. I would love to see an attack on this scheme. I really would. You know, I've had this feeling for a long time that, you know, just because of looking at the early history of multivariate, that the idea of multivariate encryption should be offensive. We should be offended by this. They shouldn't exist. But I'm having a harder and harder time keeping that feeling. There are interesting ideas coming now. And I'm actually very looking forward to Daniel Kabarkas's talk next. He makes ZHFE into something efficient. They've also done a little bit of work with my minus stuff. I don't know if he has anything prepared for that or not, but they've also done a little bit of work on this and messing with the co-rank of the L's for key generation. But it's exciting. It's exciting. Thank you.
Any questions from the floor?
Just to prepare Daniel's talk, what is the timing for generations to generate the
Oh, for the original one? For the original? I don't know. I don't know. I don't know. I don't remember this. I'm sorry, I don't remember.
And just a quick question for you. So you suggest the minus, right?
Yes.
What is your minus? What the minus number should be?
The minus number, what it should be? No. The minus number is specifically this thing that I did, just literally removing 2.
Just 2.
It is literally just 2.
So why not 1? What's your exact?
You can do 1. No, actually, so the difference between 1 and 2, here's my idea for that. So yeah, this is a very good question. It's a very good question because if you remove 2, then you're definitely cutting down on your entropy more than you would be if you're removing 1. Entropy in your key space. That's definitely true. The reason I like removing 2 is because I can think of it symmetrically as removing an equation from F0 and removing an equation from F1, and then it makes the scheme look as if it's a small field scheme. You know, there's literally not in the maps that I'm publishing to you anything that has to do with the extension field. Only this relation with psi, which is elsewhere. So you're not even seeing that extension field in those maps. That's really the only reason.
I'm still a little bit worried about the property found about this low rank, right?
Yeah.
So might have to do a little bit more. I mean, what's the rank you want to achieve? And suppose we are looking to make like
You want it to be pretty high. I selected these parameters at the end with 3 as the co-rank for every one of those L's because I was thinking that would put the Q rank right at the borderline of what we should be able to do. Which I think should be on the order of, I don't remember what I had. I have it written in the paper. So you can look in the paper. I don't remember off the top of my head.
Okay, well, let's thank Daniel.